And we are going to turn the floor over to Dean Wells, who has been around Microsoft on and off for a good number of years now, after a brief stint doing something with, what are they called, those rectangular objects with pages we all used to...
Oh, I can't remember.
It starts with a B. The things that came before Kindles. Any case, let's give Dean a warm welcome. Come on, warmer than that. A little warmer. Okay, too warm, too warm, too warm. Now it's all going to go to his head.
If that's your idea of warm, I'd hate to see what it was like when it was a cold welcome. All right, my name is Dean Wells. I'm a program manager in the Windows Server team. Specifically, I work on assurance technologies. What we're going to be talking about today is specifically what sort of attacks are unique to virtualization fabrics. Obviously, there is somewhat of a bias here toward Hyper-V, but these attack vectors are pretty much universal. They'll work on VMware and the rest of the field as well. So why focus? Well, the reason for focusing on this is because there are attack vectors, as I said, that are unique to the fact that you're running a workload on a virtualization fabric. Then I want to give you a checklist of the requirements to build one. If you wanted to build a guarded fabric, something that could protect itself from these attacks, what would a sort of high-level checklist look like? Last but not least, let the attacks begin, and I'll walk you through a slew of attacks. We can't do them all. We've got about 12 in total that we show. I'm going to do about 6 or 7 here and show you how we mitigate them. All right, first things first then. Take a look on the left side. This is the side of the industry that I'd say got most of the attention for a decade, possibly even longer. The right side of the board, though, where we've got compromised fabrics, easy to copy or modify VMs without notice, can't protect a virtual machine with gates, walls, cages, and security guards. Who did anything here? Precisely nobody. The entire industry had its head in the sand, except for us. We finally decided to do something about this, and I'll show you what that is a little bit later. By the way, if you think I'm talking fast now, see what happens when there's 2 minutes of the session left. All right, first, the solution's high-level requirements. A place to run sensitive virtualized workloads that's free from malicious software. I know I shouldn't say this because it's being recorded, but that one falls into the no shit category. That's the one we really do have to get nailed. A way to verify that the host is in a healthy state. Absolutely, that would be useful. A process to securely release keys, and only to do so to healthy hosts. And last but not least, management tools to automate the secure provisioning of these virtualized workloads. So on to the attack. Let me first introduce a couple of nefarious characters, though. Anyone know this face? I know he's handsome, boyish looking, but he really is a nasty piece of work. Taylor is one of my peers in the Hyper-V team. He owns containers. In this particular guise, he's going to be our fabric admin, and he's going to be readily bribable with thin mints and various other things. This guy is just permanently angry. Anyone here know Ned? A few of you are raising your hands. Okay, nobody's going to argue. He is angry a lot. He is going to be our storage admin. So here's attack 1. Ned wants a raise. So he decides, having his background in storage, SMB, and Active Directory, that he's going to give himself a raise by simply going ahead and stealing the HR and accounting admin's Active Directory passwords and then making the modification himself. How does he do this? Because there's a virtualized domain controller running on a Hyper-V host who's storing its VHDs, VHDXs, VMDKs, I don't care what hypervisor it is, on Ned's file servers. Subsequently, Ned has access to it. So, rolling the demo forward. See, look, made out of fabric, very clever. That was subtle, took me weeks to come up with that. Here's the attack. Steal a user's password from an offline copy of a virtualized Active Directory domain controller. This virtual domain controller runs on a Hype host that uses an iSCSI target stored on a file server over SMB3 to mount the disk locally so that it's got nice fast access to storage that's managed by a different team. So the first thing that Ned does is he takes a copy of that and puts it into his Scratch. Since it's a VHDX, he mounts it. He locates the VHDX of the Active Directory domain controller and mounts that. The first thing he then does is use these DS internals calls, or disinternals as I like to call them. These DS internals tools have been around for a while, and now they've gone ahead and built PowerShell modules around it. Thank you, Lee Holmes. Much appreciated. All we're doing here is we are literally extracting the system key out of the system hive. We're then using that system key to decrypt Active Directory's password encryption key and then dumping all of the now unencrypted password hashes. Can anyone say pass the hash, brute force attack, whatever I want to do? I can walk off with this. How long do you really think with that list it's going to take me to get something that's useful? Not too long. How do we mitigate that particular attack? How would we mitigate that? Well, here's one. How about we encrypt the storage using keying material that's only available to the virtualization host? That way, it's not encrypted by Ned's device that Ned has the key for. It's encrypted by the Hyper-V host or by the VMware host. So let's reset. I love that animation. What a fantastic transition. You go, PowerPoint. That's the best and only good feature you've implemented in... No, I won't say that. That's rude. Sorry, PowerPoint. I love your product. So mitigation's in place now. The virtual disk files are stored on encrypted volumes. And the encrypted volume is actually being encrypted using keying material that's held on the Hyper-V host, i.e. Ned doesn't have it. So Ned decides to collude with Taylor, offering him a box of Thin Mints and some increase in salary. And then because Taylor can log on to the virtualization host, Taylor can log on at the Hyper-V host. He's a Fabric admin. Of course he can. He lives inside the encryption bubble. That encryption is transparently removed from Taylor's perspective. So Ned bribes Taylor with the Thin Mints, the promise of a huge raise, and the attack proceeds exactly as the same as it did before. So let's just take a look at that one rolls through. It does get different in one other place. We now don't need to mount the iSCSI target. We simply go straight to what we see as a local VHDX, copy it. We could take it home or we could execute the attack here. It doesn't really take very long. I mean, look at the size of these VHDXs. I can fit these on a USB stick. I can put the entire dump file of a virtualized domain controller on a USB stick. But this time, when they try and mount the file system, they cannot do so. So Ned was blocked. So we switch over to Taylor. We're now on the Hyper-V server. BitLocker provides no defense here because we're now logged on, again, with inside that encryption bubble. This is the Hyper-V server's key. It has the key. It can decrypt the file system. And the attack continues exactly as before. I won't go through the same boring stuff there because you've already seen it once. So my general guidance here would be fire both Ned and Taylor. We will repeat that guidance frequently throughout this course. And then move the file system encryption somewhere else. The first problem was there was no key, or the key was on the SAN, so Ned had it. The second problem is the key is on the Hyper-V host, so it's with Taylor. Well, Taylor shouldn't have natural access to virtual machine workloads merely because he's the Fabric admin. Those two are not the same role. So why do many companies absolutely refuse to deploy Active Directory domain controllers on Fabrics, on virtualized hosts? Because they know these attack vectors exist. We set out to solve them. So we can move the file system encryption inside the guest. And we'll do that by using a BitLocker boot passphrase to unlock the key. That's the BitLocker key protector. That allows it access to the FVEC, the full volume encryption key. And from there, the machine can boot up. So we reset. We got those mitigations in place. Ned's given up, but Taylor still wants his new car, so he wants to get that pay rise. He abuses his Fabric admin permissions and adds a new bootloader. Let's call that Tayloader. So what does he do with this? He basically creates an ISO containing malware that's got boot componentry in it that looks like the BitLocker boot screen asking for the BitLocker password. And he adds that to the VM and then waits for a natural servicing window to occur. Once that natural servicing window occurs, Taylor's going to go ahead and have the virtual domain controller owner console into the VM, enter the boot passphrase, and unlock it. But what they're really doing is they're going to end up entering that boot passphrase into Taylor's nefarious rootkit that looks and behaves exactly the same way that the BitLocker passphrase screen does. So we'll see that in a second. We're showing you the mitigation here for the last one, by the way. I forgot we were doing that in this video. So that one there is showing that we're now unable to mount the disk because the virtual machine itself has possession of the key through the boot passphrase. That was what that first one was doing. Here's Taylor now going and accessing the settings of the VM. He's going to browse through to this malicious ISO file that contains necessary boot media and his little rootkit of sorts that presents a screen that looks exactly like the BitLocker entry screen. And finally, he verifies the DVD device has boot priority. He says OK. He now waits for this natural servicing window to occur. He claims that the VM has been shut down for backup purposes, patching, whatever, at which point it reboots. He then contacts the virtual machine owner in the Active Directory or identity team and has them enter the password, which they did directly into his bootloader. He stores the password away somewhere wherever he chooses, and they then inject that passphrase into the natural Windows boot sequence, and the domain controller comes up as normal. How many of you have thought of doing that as an attack before? Okay, all of you with your hands up should be fired because you're clearly nefarious. So move along. Right, so we're still going with our recommendation here of firing both Ned and Taylor. Advice this good rarely needs changing. And we're going to move on to a modern hypervisor. Enough of all this break-fix drivel. This is a little bit silly. We need to do better with our virtual machines than we're doing here. How about we offer virtualized UEFI firmware? Secure boot, measured boot. Measured boot implies another device, a synthetic TPM. We can do all of these things now. So let's reset and imagine that we've got this list of mitigations in place. So the virtual disk files are stored on encrypted volumes. The VMs are encrypting their own volumes using a boot passphrase. And the modern hypervisor that can provide its VMs with secure boot and TPM-backed key release is now in place. Do we need boot passphrases anymore? We'll see in a second. So Taylor decides that with all this in place, I've got to get a bit more modern. So Taylor's now going to use a tool written by Mark Russinovich, thank you, Mark, for making our hypervisor subject to different attack vectors, called LiveKD. LiveKD is going to attach to a worker process running on the Hyper-V host. It's going to dump its memory, and what do you think Taylor's going to do? He's going to take the dump file off, walk home with it, and spend the next 3 hours, 3 days, 3 weeks, he doesn't care how long it takes, to extract the full volume encryption key from that dump file using publicly available tools that can be downloaded from the internet. This is why virtualization fabrics need additional security. They provide attack vectors that are unique to them. You can take a dump of a virtual machine, and you could probably manage to copy the virtual machine reasonably quickly, bring it back up, and just say, sorry, we lost the network connection for a little bit. You can't really do that with a full-on Active Directory domain controller running on bare metal that's in a data center in a cage with padlocks and two cameras focused. All of those good things work for physical bare metal boxes. They don't do much for virtual machinery. So in this case, let's show you what this attack looks like. So the Fabric admin wants to steal the secrets from a VM. They know the VM's now encrypting its own disks, so they attempt to steal the VM's encryption key by using a debugger. So the first thing we're going to do is use this volatility framework and LiveKD. LiveKD gives us the dump. And yes, I sped that up because that was rather boringly long. And then we sit there and we basically run this volatility framework. We tell it to use the following plugins against 2012 R2X64 and go and find me the BitLocker key. This was many, many, many minutes later, way longer than this entire session. That's what it spewed back. It just outputs every single copy of what looks like or appears to be an FVEC, or a full volume encryption key in memory. Since they're all the same, I think that's a fairly good indication that it found the right one. At this point, I'll use tools such as, I think it's called disinternals or something like that. It's a Linux utility. And I can then just inject that FVEC, mount the disk, and take the data off as I see fit. So, again, we still fire Taylor. It's extremely necessary at this point. We implement code integrity now. We're at a point where he seems to have bypassed everything that we've tried so far. So how about we use code integrity policies to prevent him from running nefarious tools? That seems reasonable, because a Hyper-V host should be running on an OS that is very locked down, say server core. It doesn't have a plethora of tools on it. It doesn't have Chrome or Firefox, per the earlier demo. It doesn't have hardly any tooling on it at all, except what's necessary for a Fabric admin to do their job. So let's go ahead and reset. We now have all of those mitigations in effect, and we're now going to see that Taylor recognizes a code integrity policy is in force, dislikes the fact that a code integrity policy is in force, and abuses his local admin privilege to remove the code integrity policy. So let's show you how that's done. So he's after the same thing again, some generic secret, could be a SQL database, could be an Active Directory domain controller. AD is never really the target, it's usually just a means to an end. Here he tries again to go and dump the virtual machine, but LiveKD fails. The system cannot execute that because the code integrity policy, enforced by the hypervisor and then by the kernel for user mode components, isn't allowed to run. So code integrity was actually reasonably successful. But Taylor's an engineer, and he knows how code integrity works. So he went into the code integrity folder, and he renamed the sipolicy.p7b, that is the compiled code integrity file in a cert format. He renamed that, moved it to the side, rebooted the system. What code integrity policy is now effective on this computer? None whatsoever. His Hyper-V host no longer has a code integrity policy, and he's off to the market again. Taylor's annoying, right? So this firing thing still stands, I say. Sign and lock the legitimate restrictive code integrity policy to UEFI. What the hell does that mean? What it means is we have a mechanism now where we can lock a signature of the code integrity policy into a UEFI secure variable that is read-only once UEFI transitions control to a bootloader. Hence, it can't be easily or readily changed after the fact. I would imagine, once the world starts doing this, that somebody in the central IT department would configure a code integrity policy, and then as that machine is deployed for the first time, somebody trustworthy in central IT would lock the policy and store it in UEFI. Okay, that's what we're going to do here. Let's see if this thwarts Taylor's attack. The Fabric admin attempts to bypass CI policy by replacing it with his own. But the Fabric hosts had their policy locked to a UEFI secure variable. So let's see what happens when Taylor tries the same attack again. So in this case, he locates the pre-configured CI policy that permits the malicious tools. He's going to go ahead and locate the code integrity policy, and he's going to delete that one and replace it with his own. Arguably, he could delete that one and leave no policy on the system, but in Taylor's mind, it's probably better for a code integrity policy to be present in case anyone is checking for that. Maybe they're not checking for what the code integrity policy enforces. So here is now a very, very small code integrity policy that permits just the malicious tools and the Windows binaries that Taylor needs. He has to reboot. He does so. Uh-oh. As soon as Windows boots, as soon as we get far enough through that boot path, which is very, very early, we try to slurp up the code integrity policy. We get its signature back. We take a look at the locked UEFI variable. If the two don't match, we blue screen, or black screen, as the case may be. That is a conscious choice on Windows' part there to do that, because it is considered to be better for that workload to fail than for that workload to work while being susceptible to attacks or stealing secrets. It's a conscious choice that an administrator makes. You do not have to do this. But arguably, that's a pretty good thing to do on a fabric where fabric admins can overstep their bounds and start stealing secrets from the virtual workloads running on them. Last but not least, attack number 6. Taylor's run out of options, but he's quite forceful here. He's going to take a greater risk now. He's actually going to call a crash dump of the entire host. So by crash dumping the entire host, he's very much revealing himself. So he's kind of desperate at this stage. He must get paid absolute pittance to keep on this much. So this is similar to the VM-specific dump, except it's the whole host. Okay? So let's see exactly how he's going to do this. So he knows that he's got signed CI policies in effect. So he restored the CI policy using an offline restoration of the CI policy. That's the only way of getting it back to boot. He then tries to bypass all of these systems by simply crash dumping the Hyper-V host. So he ensures that crash dumps are switched on and configured for a complete memory dump. This does include all the virtual machine pages. It doesn't include the hypervisor itself, but it does include VM memory. And the fabric admin then triggers a crash dump. Boom, he does that using an NMI, and he's got a nice crash dump file that he then copies off and takes home with him. Now all he's got to do is figure out where's the isolated VM worker process in there and all of its memory, take that out, segment it, and then use the same tools he did earlier on to go through, find the FVec, and gain access to the BitLocker encrypted volumes. So yet again, he still found a way around it. There's only one solution left, really. We have to be able to ensure that this host can't do anything because it lacks keying material before it has been attested, measured, thoroughly measured, as healthy. That's what we're going to do now. So we're going to configure the host to disallow, or if they are allowed, we're going to configure it to encrypt memory in the crash dump. We're also going to measure the keys, because there is no point in measuring that crash dumps are on, and if they are on, we must then measure that they're encrypted, and if they are encrypted, if we don't measure what the keying material is, that would be pointless, because now the attacker would use their own keying material and encrypt it with a private key they have. No sense at all. So we measure all three things. If it's on, we measure it. If it is on, we now need to say, is it encrypted? If it's not encrypted, fail. If it is on and it is encrypted, measure the key and compare it to a known good set of keys. So this is now all done with an external health attestation authority, and we're going to couple key release for those virtual machines to that health attestation dance. So let's go ahead and show you what this demo looks like. So the fabric admin, once again, attempts to obtain a crash dump on a host that's being measured and attested. Taylor doesn't really know what this means. We're outside of Taylor's world now. So the first thing that the fabric admin needs to do is power on the VM, because he's got to get the VM's FVec in memory for the crash dump of the host to be useful. But he gets an error saying that the key protector couldn't be unwrapped. This is basically saying that that is protected by an asymmetric key pair that protects a symmetric key. Taylor doesn't possess the private key. That was on the external attestation service. You can see it failed him because dumps were enabled and dump encryption was not switched on. The external attestation service will not permit this. So if we review every single thing that we've done here in terms of high-level mitigations, we've got virtual disk files that are now stored on encrypted volumes, VMs that are encrypting their own volumes, modern hypervisors that are providing VMs with UEFI secure boot and with synthetic TPMs. We've got restrictive signed, UEFI locked code integrity policies, external health attestation components, and tightly coupled key release to that health attestation dance. All right, so more specifically, what do we actually need? We need guest UEFI secure measured boot, per VM synthetic virtual TPM, signed template disk, secure VM provisioning, forward secrecy, hypervisor enforced code integrity, secure key release, host UEFI secure M measured boot, crash dump protection through measurement and attestation, strong TPM backed identity, per VM encryption keys, and encrypted live migration traffic with forward secrecy. Now, wouldn't it be fantastic if somebody bothered to build a product with all those things in it that worked? Oh, God, we did! And there it is. Windows Server 2016, guarded hosts and shielded VMs. I didn't even show you some of the things that this thing protects against here. We also protect provisioning disks, template disks. So there's secure provisioning where we take a template disk, a known trustworthy admin signs that template disk, and then that gets added to the VM owner's encrypted lump of secrets that we call shielding data. And at provisioning time, attested as healthy, host will validate that the signature of that template disk matches a trustworthy signature to ensure that the template disk has not been pre-infected with malware. Otherwise, you'd be deploying a shielded, malware-infested virtual machine, which would be pointless. So we've got additional protections in place. I didn't even have time to show you here. I think we had a question there.
I did. How do you protect the state files? Because I've done what you do, and I just take them from the state files. I take the keys out of the state files.
So all of the state files are also encrypted.
Okay.
Same basic key, so we basically derive a key from a transport key, and then we encrypt them. And then the transport key is rolled to a new key each interaction with the attestation service. Great question. The question there was, how do you protect the state files? It is a great question. It was the first thing we solved in terms of disk persistence. The second thing we solved, really late in the game, because we forgot about it, was crash dumps and hibernate files. Yet we literally forgot about them until quite late in the engineering cycle when somebody said, what happens when you crash dump the host? And we're like, yeah, you can just extract all the keys. Fabulous. Let's encrypt those. So that came in rather late in the day, but before the RTM went out the door. So that's in there as well. Any other questions?
I'm curious if you've surveyed any of your major...
That's eerie. Where's that coming from?
Far left, or you're right.
Oh, there we go.
There
Great.
you go. I'm curious how many of your large deployment customers you've surveyed for the feasibility of actually deploying this full set of features.
So the question there, I imagine you're basically hearing is, how many people have deployed this based upon a perceived level of complexity? Well, the largest customers that we've got looking at this right now are all governments. I won't be no more specific than that. There are obviously governmental agencies, military agencies that are deploying this as well. The biggest blocker that we're seeing right now isn't the Hyper-V host, it isn't the shielded VM, it isn't the slightly different deployment semantics and signing of template disks, creation of shielding data, all the primitives that build a shielded VM. It's that host guardian service. The host guardian service is an external attestation and key release mechanism. It would typically be backed by an HSM, a hardware security module for key release, but it needs to be managed with the same kid gloves as you do domain controllers and PKI environments. It even uses PKI for its own purposes. We've heard that feedback loud and clear. We're working to build an HGS as a service, so it would be something that runs in Azure, and you can simply point Hyper-V host on-prem at a RESTful endpoint in Azure over a TLS, and it will go ahead and do the attestation dance for you there. So does that answer your question? Most of them are not happy with the HGS side because they claim it's a little bit too much of a burden. Those that are happy typically have an Active Directory forest called an ESAE forest, the Enhanced Administration and Security Forest that the MCS guys put together. They combine HGS with that forest, and that tends to be an unblocker. But that is the feedback that we're hearing. The host guardian service needs to be slightly simpler to deploy. Any other questions?
Perhaps the most amazing thing is if we gave Dean a full hour, he just does the same presentation over again, backwards.
Excellent. Just reverse it, rewind. Question at the back there.
If I change my signing policy, how hard is it to revalidate, or is there a process to revalidate that signing process?
The signing of what?
Code signing. So I change my code signing policy or update it.
Are you talking for code integrity purposes?
Code integrity, correct.
Yep. It's, you can merge CI policies together. So the question there is around the certs that are being used to code sign the binaries that are permitted to run as part of the code integrity policy on the Hyper-V host. Yes, we can merge new CI policies on top of the existing one in order to bring new CI into play. I won't say it's the easiest thing to do. There is a commandlet, however, to do it. But yep, it's definitely doable. Any other questions?
Last call before we reset for our next presentation.
Can't believe I got that into 25 minutes.
I
How many of you understood more than 7 words? All right, thank you very much.